All right, so it's great to have Dan Sheehy from North Carolina State University today, who's going to be talking about the persistent homology of Lipschitz extensions.
Okay, thanks so much for having me. I'm really excited to be here virtually, particularly because this is the first time I presented this work. So this is something I've been like wrestling with for a while, and I thought this would be the perfect setting to kind of workshop some of these ideas. And so in particular, there's some concepts I'm going to present today that I expect probably appeared in one form or another in the literature previously. So like if you think of some references, please put them in the chat, especially with respect to something I call a sub-barcode. All right, so I'm going to talk about persistent homology of Lipschitz extensions. This is not Lipschitz extensions of persistent homology, which is a different thing. Okay, so if you're familiar with that work, not doing that. All right, so let's just jump in. Here's the setup. I have some idea that there's some ground truth function on some space X, right? Later, maybe this will be some metric space, and it's a real valued function. And I get some data, which is just a subset of X, and I get the function evaluated just at the subset. Okay, so you could think of this like S is a subset of X, and I was given F restricted to S. Okay, so that's kind of what I get as input. And my goal, or at least the standard goal in a lot of TDA would be, I should try to compute some approximation to the persistent homology of this function. That is, let's say the sublevels of the function. And that approximation here is in terms of the bottleneck distance usually, right? Or interleaving distance if you want to think of this just as the module. And so I think this should be familiar to many of you, right? Like that's the game, right? So maybe if you're just thinking about distance functions, right? It's an unknown distance function, and maybe most of the unknown is about the space. Or maybe you know something about the space, and it's just that you only know the function values at some small set of points, in which case it looks more like these results on like scalar field analysis or like persistent space clustering. All right, so that would be, I would say, the standard goal. So what I'm going to do in this talk is I'm going to present a very different kind of goal that's much weaker, right? So instead of trying to get this bottleneck close approximation, I'm going to compute what I call a sub-barcode of this barcode of the sublevels of F, right? The persistence of F. Okay, and I'll tell you what this means. But first, let me tell you what the big idea is. Now, a priori, you might say, okay, you have some method of doing data analysis where you produce barcodes from data. And so you might say, well, if I only have some of the data, maybe I should be able to compute at least some of the barcode. And so what I mean by some of the barcode, I'll give you a formal definition in just 1 second, but you can think of it like I had the bars and I just threw some out and shrunk some, and the result was a sub-barcode. Okay, so formally, if I have two barcodes A and B, then A is going to be a sub-barcode of B if I have some injective map from the bars of A to the bars of B, where every bar in A gets mapped to a bar that contains it as an interval. Okay, so I really wanted to call these sub-diagrams so you wouldn't have this two B's in a row, sub-barcode, but the intuition really has to be done in terms of bars. And here's the picture. So like I've got a barcode in black, that's A, one in red, that's B. It's a sub-barcode if I can match every one of the bars into some bar that contains it. So I can kind of show you, like, you know, there's some, this bar is actually contained in the bar that it maps to. And like kind there's some bars that are just extra in B. That's fine. And so when we have this relation between barcodes, we're going to just use this kind of partial order notation. In fact, it does give a partial order on barcodes. As far as I know, I haven't seen this used. Does anyone want to shout out some cases where they've seen this concept? Because it seems like a natural one, and you'll see it arise very naturally, but somehow it doesn't happen. But we'll see. So if I have this definition, before I tell you how we're ever going to compute one of these things, let me tell you what it would be good for. So if you imagine that you're doing some kind of classification, in particular, if you want to do falsification, that is, you've got some hypothesis. You say, you know what, I think that the underlying function had a particular barcode. So I know this, I have this barcode B in mind that I think maybe my data came from. If I could compute a sub-barcode straight from the data, I could check to see if that sub-barcode I computed is in fact a sub-barcode of the ground truth, right? So I can check if B prime is contained in B. And if not, then the hypothesis must be false, because it really, if I had a guarantee that it really is a sub-barcode according to the data, right? That's how I can falsify this hypothesis. And of course, that should feel good to topologists, because in some sense it says that you can do the thing that topology is really good at, which is to separate spaces, to identify differences. Right. So that just leaves this one small question, which is like, how do you actually do step 2? How do you actually compute something that's guaranteed to be a sub-barcode of this ground truth? I would say that there's one case where it's really already well known how to do this if you make some pretty strong assumptions. In particular, if you have enough assumptions so that you can guarantee that you can compute a barcode that's bottleneck close, like you have that much stronger condition, then you can shrink all your bars. If you're epsilon bottleneck close, you could shrink all your bars by epsilon, and that will be a sub-barcode. You can think about that one. But I want to get rid of a lot of those strong hypotheses about what you need to know about your sample. And so, like, you know, I might completely miss some parts of the barcode, but I might still get enough to falsify a hypothesis. Okay, so this is the motivation, or maybe how to start thinking about this. If you, I'm guessing the RIPS seminar has seen RIPS check interleaving, I'm going to say at least once. So if I've got my C's here are check complexes, my R's are RIPS complexes, and you know, it's quite common to have this kind of interleavings between RIPS and check complexes. And for me, as a graduate student, when I first started kind of reading papers about persistence, one of the really great papers, early papers that I think all grad students should read, was this paper by Fred Chazal and Steve Udo on towards persistence-based reconstruction. It's actually the paper where the persistent nerve lemma first appears. And but one of the things that was really useful for me was that I got to actually wrote a paper with Steve later, and so he was able to explain to me really a lot of these ideas about how to use functoriality to go from statements about complexes, or in our case, I was really thinking about statements about geometry, to statements about homology. And of course, that's a kind of, for a computer science PhD student at the time, that was a big hurdle for me. And so in that paper, you get essentially diagrams like this, where if you put the right geometric hypotheses on the underlying space and on the sample, like you have a nice, really dense sample, you get something like this, right? You get something like the underlying space is isomorphic to the check complexes at all these scales. And so this would be like, you may have heard of these conditions on the geometry, like bounded mu reach or bounded weak feature size. You get a slightly different diagram for that one. But where you can assume that, okay, at some small scales here, I can look at unions of balls, and those unions of balls, their nerve will all be isomorphic in homology to the underlying space. And so, and also not only that individually, but also the maps between them, actually the inclusion maps give those isomorphisms, right? That there actually are, these actually come from deformation retractions from the union of balls to a smaller union of balls. And so if you have that, and then you have this this diagram on the homology groups, you can say some pretty powerful things, right? You can actually say that this map you got here, which is, the map in homology that was just induced by the inclusion here, that the image of that map actually is isomorphic to the homology of right here, which is actually, again, isomorphic to the space. So you can actually recover the homology of the space in those situations. Pretty good. The way this proof goes, well, it works by looking at the ranks and looking at how this map factors through these other spaces. So if you were to ask the following questions, like, what if I only knew a little bit? Like, what if I only knew this part, right? I just knew that I could take this kind of interleaving. What you would get is that just an upper bound on the dimension of the image, right? So this triangle here gives you an upper bound on the dimension of the image, and in the other direction, like the bigger piece, gives you the lower bound. And then since the dimensions are equal and they're just vector spaces, right, they're isomorphic. And that's actually how the proof goes. So if I only knew like this, if I just said, look, I have these two RIPS complexes and they're nested. And if I look at the image of that, the homology of that image, well, the result is at least going to be a subspace of the space I care about. And so this is the analogy I want to push on, right? That we're going to say, okay, I'm going to do something similar, but with persistence modules, and the result will be I will only get a sub-barcode. All right, so let's see. It's not, at first I thought this was easy. And so I have this theory that most interesting results go through this process of like obviously true, obviously false, and then they non-obviously true. And so hopefully maybe you might go through that process here. So if I replace these vector spaces with persistence modules now, and these are, I have these homomorphisms between persistence modules, then it turns out that if I look at the barcode associated to the image persistence of this homomorphism, it's going to be a sub-barcode of Y. Now, it mostly, if you want to prove this, it's not too hard. I'm not going to go through the proof. It comes, I think, actually we have a couple different proofs of this, but one of the nicer ones uses this notion of an induced matching from Uli Bauer and Mike Lesnick. And roughly, this is a cartoon, but this will kind of give you the rough idea of what happens, is that if I had, let's just say I had only one bar. And so this picture right here shows a barcode, 3 barcodes, each with only one bar corresponding to 3 different persistence modules. When you take the image of a homomorphism, the result is there is some matching of the bars such that the barcode of the image matches up the bars and you get the intersections of the 2 bars. So actually the map from X to Z, if it matches them right, it will be this intersection of the bar in X and the bar in Z. Now you have to be super careful here because when you switch from persistence modules to barcodes, right, it's not functorial. So it's not obvious, or it's not even true necessarily that the matching you got from bars in X to bars in Y and the matching you got from bars in Y to bars in Z will compose to the matching you got from just taking the map itself. So you have to be careful, but it happens because we're looking at an image here. It's a special case where this actually does work out. All right, so again, maybe if someone has a question, they can stop me on here, but this is going to be the key step where we're going to actually leave persistence modules and go to barcodes, right? So if we can make this claim about persistence modules factoring through another persistence module, we're going to get a result about the image as a sub-barcode. All right, everybody okay with that? All right. Okay, so now I'm gonna have to lay out a bunch of definitions here. I'm gonna say that X is a compact metric space. It's not super important that it's compact. It's useful for simplifying some stuff. And I'm going to take Rx here is actually, this is going to be the poset of Lipschitz functions on real valued Lipschitz functions on X. So when I say it's a poset, I'm going to do a pointwise partial order. So like one function is less than or equal to another function if it's less than it at every point in the space. Okay, so this is a very simple way to define partial order on real valued functions. And again, just to, in case you haven't seen this, so Lipschitz means that the distances between points doesn't increase in the function. So if I'm mapping into R, right, the metric on R is just the absolute value of the difference, right? So the difference in the function values is at most the distance. You might call these one Lipschitz functions because there's an implicit one in here, but we'll just call them Lipschitz functions. And for real valued functions, you can break apart this absolute value into two different statements, right? One being that f of x is less than or equal to f of y plus the distance, and the other being, so this is an upper bound of the function at x, and this is a lower bound where it has to be greater than f of y minus the distance. Okay. In fact, we're going to use these upper and lower bounds to construct other functions. All right, so that's the poset of Lipschitz functions, and it's nice as a poset. It's also a lattice. We'll maybe get into that. All right, and now, so if I have filtrations now, I'm going to think of just filtrations. They're going to be functors from, so let's say the R to top. And so it's going to associate a topological space with each real number. And if I have two real numbers that are ordered, like s less than or equal to t, then there's going to be a corresponding continuous map from the space at s to the space at t. I'm going to look, if I have a function, I would like to have a filtration. So the way to get filtrations from functions, I think the most common way it's done in TDA is I'm going to take sublevels. So all the points in the space whose function value is less than or equal to some alpha will be the space in the filtration at alpha. But I'm also going to think of this functorially in terms of this poset, right? So if I have two functions that are ordered, like if f is, let's say, less than or equal to g, then the sublevels of g are going to be contained in the sublevels of f. So this is contravariant in the sense that so smaller functions are going to have larger sublevel sets. And so if you have, if at every scale, you can include the sublevels of one into the other, that also gives you a natural way to map one filtration into another. We call this an inclusion of filtrations, if you like. All right. And I'm just going to use this notation here. This is not a functor, but I'm just, when I tell you that I'm going to write like the persistence of f as the persistence of a function, I mean the barcode of the homology of the sublevel filtration of f. And if I now have an ordered pair, like if f is greater than or equal to g, I use greater than or equal to because of this contravariance. So if f is larger than g, then I look at the barcode of the image of the homology of the inclusion of the sublevel filtrations. I know that's a lot. So I just like threw a bunch of definitions. Are we good? Anyone want to slow me down? All right. Okay, so if I have these definitions in place, I need one other thing, which is these Lipschitz extensions from the title. So given a function defined only a subset of points, there's a maximum Lipschitz extension. It's essentially taking the minimum of all the upper bounds. So it might seem odd that the max extension is defined as a min, but it's the least upper bound. It's in fact, in this notation I'm going to use here, it really is, like if you're thinking about posets and lattices, and you think this looks like a join, this really is the join of all Lipschitz functions that agree with the data, in fact. Right, so if I only know, a question, yeah.
Yeah, so are we assuming that the f has constant one, Lipschitz constant one?
Yes, we're going to only deal with one of those. You can, we can, if you pick a different Lipschitz constant, you would, put it right in there. And actually, everything is fine. Or the reason I don't specify, if you knew a Lipschitz constant, then you could also just scale the function.
I see. Thanks.
Everything would come out the same. All right. So in pictures, right? So if I had this function on the line, and I only knew the function value at these points, right? Each one of these upper bounds is like these cones, and the function, the Lipschitz extension, the max extension, is just the lower envelope of these cones. Okay. And similarly, we can use the lower bounds to give the minimum Lipschitz extension, right? So I'm taking the function values minus the distances. So it just turns everything upside down. Right, so I get each point gives me a lower bound. And one way to think of this is that if I assume the function is Lipschitz, if you tell me the value of the function at one point, it puts some constraints on what the function can be, because I know it's Lipschitz, and now the function value at every point can't differ too much from that one point I know. In fact, it can't differ by more than the distance. Okay, so this gives me two different ways of extending the function I had, right? The value, the function I have at the sample to the whole space, right? So I get these two different extensions, and it hopefully, because of the way we constructed it, it should be clear that the minimum extension is certainly less than the function, because it's less than every Lipschitz function that agrees with data, which is less than or equal to the maximum Lipschitz extension. Okay, so I have this ordering, and then we're just going to put it to work. So let me now lay out the big picture. Again, I assume I have some function that's unknown, and I should mention, assuming that it's Lipschitz, etc. So that's unknown. I was given the sample S, and I knew the function values at S. And so I want to compute these max and min extensions. And so I have this ordering on the extensions. And if I can compute the persistence of the max extension into the min extension, as the sublevels of the max extension into the sublevels of the min extension, well then that will give me a sub-barcode of F. Okay, so on the left here, I've got the thing that I actually computed based on the finite data, and it's guaranteed to have this relationship to the unknown. Okay, and you can see that like actually very little is required for this to happen. Right? You can imagine cases where if you get very little data, maybe you get very little information. Maybe I'll draw a picture of this, right? So you can imagine that you just get really bad data too. Like someone could give you the data at just these points here, and you would find that, well, it looks like a constant function. In fact, I would probably get an empty bar in this inclusion. On the other hand, all I would need was just like one point up here in order to identify that this bar, or bar associated with this kind of bump in the data. All right, so there's still clearly computational challenges here, because it's not obvious that you should be able to compute these extensions, especially if you don't know the space. We're gonna have to assume you maybe know something about the space. And also you have to know enough about it to be able to not just compute the persistence of those extensions, but the persistence of the inclusion of their sublevel filtrations. All right, so so how do you compute this? All right, so here's one first step. In one dimension, this is at least not hard, right? So in one dimension, if you order the points, you will always get this kind of zigzag shape for the max extension and a different zigzag for the min extension. And the function itself will be piecewise linear in this way. And so you actually, just by, you get two piecewise linear functions defined on isomorphic complexes, which is just like the points connected to their neighbors, and then I subdivide every edge, right? So you can just actually, because piecewise linear functions are quite easy to compute the persistence of, you can also do the inclusion So I'll leave that as an exercise. You can totally do it in 1D. In RD, this is actually the thing that held me up more than anything, because this is tremendously frustrating. We actually know how to compute the persistence of the maximum extension in RD. It's not too hard to think about, because it's just gonna, if you, I guess I only drew you pictures of 1D, but even in 2D, these sublevels of the max extension are just unions of balls. So, and in RD in general. So if you have unions of balls, you say, okay, I can compute a check complex. I can at least compute a certain filtration there, and I can compute the barcode. Now, for the minimum extension, it's a little bit harder, because these sublevels are built up from complements of balls. But you can, using Alexander duality, compute the barcode there. So weirdly, though, we don't know how to compute like a single complex, for example, which supports both the max and the min extension in a nice way, so that we could compute this inclusion. Right. So that's a sort of a tremendously frustrating open question. We could talk about that offline if anyone's interested. All right, but let me tell you what we can do. And I figured this is the RIPS seminar. I'll do a RIPS version of this. All right, so I'm gonna, the reason well, let's see. It's a little unfortunate that I'm gonna have to bring in some sampling assumptions. I was hoping to never do that, right? In 1D, you don't really have to assume anything about your sample. You just say, hey, whatever data I have tells me how much of the barcode I can hope to recover. And I would love to say the same thing, let's say in Euclidean space. But for now, I'll give you what I call a semi-supervised TDA. And so here the setting is, I'm not just given my sample, I'm also given, I'm given a good sample of the space. So a good sample in the sense that it's Hausdorff close. So I've sampled for every point in X, I've got a sample within delta of that point. So I have a good sample, but I only have the function value at some arbitrary subset of the points. Right. So I had to, I don't have the data at the good sample. I only have it at a subset of the good sample. And so we're given, again, yeah, F restricted to S, and we're going to make at least this one geometric assumption now, that if I take unions of radius delta balls, that they always form good covers, right? So we can apply persistent nerves. And so here's what we're going to do. We're going to take our data, which is a function evaluated at the points of S. We're going to extend it to P. So if we assume, I guess we're assuming we can compute distances between those points in P. And so we can compute the maximum and the minimum Lipschitz extensions on the point sets, on the point set. And then we're going to use a RIPS check interleaving, and we'll get a nice big diagram, and we'll chase it around, and we'll find a sub-barcode in here. So here's how it goes. The minimum Lipschitz extension of the points, right? This is going to be a subset of the points, right? So if I think of this function, I have to shift it by the constant delta. This is to get the interleaving, but roughly you could think of this as all the points whose min extension is at most like, well, okay, this is a filtered point set, so I should tell you what it is. This is like, p hat alpha, right, is going to be the set of all p in P, such that f hat of p plus delta is less than or equal to alpha. I wrote it in this sort of shortened form, but this is what it is, right? So I put a filtration on the point set. All right, that's going to disappear. Apologies. All right, and from that, I also can get a filtered cover, which is just, the points that I have, I just take a ball of radius delta, right, for every point that I kept. So you U alpha, I should call it U min alpha, is just, I just take all the points in the P min alpha, and I just take the ball. So that's a set for every alpha. And then I can take the union of those. Right, so at every alpha, I have a cover, which is just this collection of balls. I could take the union of all those balls. And I can also take the nerve. Okay, so I'm going to use W as the union. If you want to remember it, the W, well, the union of the U's is UU, that's the W. Okay, so that's the union. And then the nerve. Okay, and this nerve, you can also think of it as a check complex. And so I do this, this is for the min, and I've got the same definitions for the max. Okay, so I've got a different filtration. The only main difference here is that I shift, when I take the points for the max extension, I shift it the other way. So I go minus delta. But all the other definitions are the same. You just have to turn your V's into wedges, etc. Hats into checks. Okay, so this is my setup, and I guess I need a RIPS complex of some kind. So here's what I'm going to do. For any scale gamma, I put a parameter here. We're only going to look at two different scales. I take the RIPS complex on the subset, again, of points at that scale gamma. So this is not exactly a RIPS filtration. You should think of it as a filtration on a RIPS complex. Like I picked a complex at a particular scale, and I filtered it just by only including some subset of the vertices. You might call it an induced filtration on the RIPS complex, where just like you take an induced subgraph by picking out a subset of vertices, and you take the maximum graph, same thing, you take the maximum complex you get from keeping this subset of the vertices. And similarly, so again, exactly the same, I've got the min version and the max version. Okay. So yeah, just highlighting. The radius is fixed, and I'm just adding points. All right, so this is our pretty standard RIPS check interleaving now. Right, so that RIPS complex, if I take a particular alpha, the RIPS complex is going to be interleaved with the check complex, which was the nerve of those balls. And so as filtrations, I also get inclusions of filtrations here, and that would be the interleaving of the filtrations. And I get that for the max extension and also for the minimum extension, right? So, the points, this is defined on just a subset of the cover here for every alpha. So you also get the inclusion of the nerves. Okay. And we assumed that our space was nice enough that we could apply persistent nerve lemma. So there are maps also, I drew them here. I guess technically they exist at maps on the filtrations, but most of the time we think of these as happening in homology, giving isomorphisms, which is going to tell us that it's going to relate this mapping between the nerves to this mapping between the unions. And then pretty much, I know that I'm glossing over this, but pretty much straight from the definition of Lipschitz and the triangle inequality, you can interleave that union with the sublevels of F. Okay, so in pictures, right, this is a union of balls. It's contained in the sublevels of the function, and then it's contained in a larger union of balls at every scale. And it was set up in some sense exactly so that this would work. All right, so now I have this diagram of filtrations, and you can look at this now, this RIPS complex at scale delta defined on the max extension, and the RIPS complex at scale 2 delta defined on the min extension. And you can look at now this inclusion, and you can look at its homology here. And I guess really this should be the barcode on the left here. Is going to be a sub-barcode of F, right? Just because, let's see if I have it, oops, is because you can also sort of map it through here. All right, and the idea again is that, well, I've got this inclusion factors through in homology, factors through this image persistence module associated with this map, which is equal to this image persistence module. which is a sub-barcode of this. Right, so I apply that kind of barcode, sub-barcode lemma twice, and you get it. And so this now means, again, this is something you can compute straight from the data, and it tells you something that must be true about the function. And the assumption now is that, okay, I have a good sample of the data, but I don't have a good sample of the function. I don't know anything about which actual values of the function I was able to, I was given. I suppose I need at least one, although I won't find anything if you only give me 1 point. All right, so the key takeaway is really this: like in the absence of complete data, you might look instead for just a sub-barcode. And this is like the key fact, right? That the persistence of the max extension into the minimum extension is going to be a sub-barcode of the function. And that's all. Thanks.
I suggest we unmute ourselves to thank Don for the great talk. Right, are there any questions? Yeah, please, Alex, go ahead.
Don, thanks for such a creative talk. So I had 2 questions that are related. So the first is, do you have a sense in how well this sub-barcode on the left approximates the barcode that you actually want in any kind of setting?
Yeah, so when you say how well, you immediately are asking back, like probably in terms of bottleneck distance, right? Or you're asking, are there other metrics? Are there other metrics you could hope for that are related to sub-barcodes? Because when you say how well,
right, so like in general, I guess, you know, you could have other sub-barcodes, just like the empty barcode would be a sub-barcode.
Oh yeah, is it crap?
Bad
I mean,
one.
that's a different question. Is it just terrible? Which is, so let me give you some examples that maybe motivate. In fact, they were the motivating examples for us. Is just, if, let's just take functions on a line. So just like if f is just r to r, if you give me a point and a point and a point, and I know that somehow between A and C, the function got large, right? Then I know that I'm going to see that. That's going to be, and what you'll see, I'll make sure to try to draw the max and the min extension, right? That somehow the max and the min extensions are very close, right? That they can't hide it. And so roughly speaking, as long as you have some data that witnesses the feature, you expect to see some of the feature.
Right. So I guess, I mean, my second question was going to be, is there some sense in which this is like an optimal sub-barcode with the data that you have? Because
yeah,
for instance,
so I would love to have a statement about that. Yeah. So I would love to have a statement about that, but I think it's probably not. It is, if you look at the lattice of Lipschitz functions, right? So you really are getting a sub-barcode that must be a sub-barcode, that in fact is a sub-barcode of every single Lipschitz function that agrees with the data. So that seems like a nice kind of universal kind of statement. But you might ask, like, is there another barcode? Like, is there a maximum barcode that's a sub-barcode of every Lipschitz function that agrees with the data? And I expect, just due to weirdness and symmetry, you might be able to come up with examples where by rearranging how they get matched up, you could get there's might be a larger barcode. Like you might, let me take it this way. If you think about saying, oh, you know, I have 2 barcodes, what's the intersection of them? Like you say, whoa, you tell me how to match them up first, right? And in a way, when you have the inclusion, it tells you a little bit about how to match them up. But you don't have to make those like choices in order to get the guarantee. And so I think if you were to say, you could define the optimization problem, like given a collection of barcodes, find the largest barcode that is a sub-barcode of all of them. But
or even just in kind of like a minimax way, like given that data is
I don't think, like, I don't know, and I my feeling is it probably is not optimal in that sense.
Okay, thanks.
See that someone else raised a hand. Hossein, feel free to go ahead.
Can you hear me?
Yes.
Yes.
Yeah, thank you very much for your nice talk. So when you mentioned this motivation, I think you mentioned this X, Y, and Z, and this F between X and Y, and then G and this composition.
Yeah.
So I was thinking of some idea. I don't know, maybe it's not okay, but my idea was to define a graph of barcodes, intersection graph of barcodes. So your vertices are barcodes and this X and Y and Z, and then you have an edge if you have an intersection. Then I was thinking that you miss the direction and the function between them. Then I was thinking that maybe we consider the idea of defining a quiver instead of just a simple graph. But it is very rough idea. I don't know it works or not. Just
so let me just, I can expand on this a little bit. So it's always, first of all, everyone should read the induced matchings paper because it both tells you what you can do and can't do when you go from the modules to the barcodes. One case where you get sub-barcodes is when you have submodules. So like if you have a persistent submodule, you will get a sub-barcode, but sub-barcodes are more general. So we got stumped for a long time because we thought we were only finding submodules. And it's also why it's not all just following from pure diagram chasing. You have to switch out and ask these questions about the relationship between bars using this kind of induced matching on bars. One thing you do get from drawing out a graph like that is it tells you a little bit about algorithmically how you might check for a sub-barcode, right? So like you can look for you can build a graph like that where you have to have inclusions, not just intersections. But
I understand.
Yeah, and you can check for matchings in that graph.
And very quick second question is that you mentioned this motivation of this minimum and maximum. So you do not consider the noise, yes? If you have if you also consider the noise, then this difference will be more transparent. Am I right?
So depends on what you mean by noise, but in one sense, this is actually something that's stronger about sub-barcodes than bottleneck distance because there is no noise in the sub-barcode, right? If it had, like, you can imagine a case where like, oh, I've got almost the same barcode, but it's got a bunch of noise. It's not going to be a sub-barcode.
Okay.
And so it kind of follows from the fact that like all the noise gets canceled out by in the image, which is not a new thing, right? You can find this in like the work on homological sensor networks. You can find this in really other kind of RIPS check kind of approaches. There are many cases where the
Thank
image
you.
handles the noise for you.
Yeah, I got it. Thank you very much.
You're welcome.
I think Bay has a question now. Please go ahead, Bay.
Hi, Dan. Really fun talk. So I have a question going back to your motivation. When you have this motivational slides where you're looking at, you give example of a sub-barcode, right?
Okay.
I wonder if you could go to that slide, so it's easier to explain.
Yeah, I think it's over here. Here we go.
Yeah, right here. So when I first see this, one of the things come to my mind is that, we have this sort of bijection between, not bijection actually, there's a mapping between a barcode and then say a merge tree structure. So you can take the bars and glue them together and that become a tree, right?
Yeah.
So now if I take what's in A, let's say that is the entire thing, I glue it into a tree, and I take what's in B and I glue it into a tree. I'm wondering if your condition of sub-barcode corresponding to some sort of subtree structure.
I think it should. That's a fantastic idea, partly because all the mappings are coming from inclusions of filtration.
Exactly.
Right.
Yeah.
So like that structure should, like you would hope that structure would also be preserved here. I have no idea how to do it, but it points you to another like possible problem, right? Which is,
Yeah.
like, is there, and maybe you know this, I don't know the merge tree literature very well, but like, is there a notion of induced matchings on merge trees?
There's, well, not so induced. There's many variations of matchings. There's, and then this is a particular one that's nice in the way that, again, this is conjecture, it requires a little bit proof, is that if your condition is always just inclusion, which in the current definition it is, that it will reduce the difficulty of some sort of saddle switches. Because I think one of the difficulty when you start gluing bars together to form the tree, when there's no inclusion relationship, that's where things become a little bit complicated, and so on. So to go back to your question, that I think there is potentially a relation of how going both ways. One is if you have sub-barcode, what does it imply in terms of the underlying merge tree structure of both your F hat, F upside down hat, right? And then there's also a relation if I going from other way around, if I have subtree inclusion, for example, does that imply automatically a sub-bar relation?
Yeah, these are fantastic questions. Let me tell you, one of the things that complicates it is that we don't actually know what this mapping is, right? So the proof is an existence proof. Yeah. So even when we compute it, we don't know. Obviously, in the case where we get a guarantee with respect to something unknown, obviously we don't know it. But even if we knew it, we don't know it. Right? Even if I knew what F was, I don't know actually what the matching is, because like when you go through the induced matchings, right, you just get the existence of bars sometimes, and as we do it, like I think the proof might even give, in some cases, like in a whole equivalence class of matchings. It doesn't even necessarily pick one out. Right,
but I'm saying like, if I come from, so my other perspective is that in your proof later, right, you actually build some, in some sense, the interpolation of this function, either with the upper envelope or the lower envelope kind of thing.
Yep.
That is known to you as data, right? So that is something you could compute. I can compute my persistence. I can also compute my merge tree, right? Those are known to you. So now one way to think about it is kind of cheat a little bit by saying that, okay, I am going to apply some form of tree matching, but that tree matching is going to be, of course, constrain your search space a little bit. But what that's going to give you is potential a set of candidates that contains maybe a good set of your sub-barcode matching, right? So in some sense, I'm constraining it to a smaller search space, and then with the hope that you can find some of those maps. So
so if you have two filtrations and one is nested in the other, that is at every scale it's contained, does that give you, that gives you does it give you a mapping from the merge tree of the one?
I have not thought about it carefully yet.
It should be contravariant as well, right? It should be like, if I'm containing the other one, I should have it should be, if the filtrations are nested, then I should have, you would hope, but I don't know, like it seems.
Yeah, I think it takes a little bit of time to think about it, but my point is that when I see this picture, I see an immediate connection to the merge tree structure, and then there's maybe a nice relation.
I love it. I don't know. I hadn't thought about it at all, but I think there could be something there.
Yeah.
Henry, please go ahead.
Thanks, Don. I had a question. So let's say I suspect that my function is somewhere between 1 Lipschitz and 5 Lipschitz. Do I sort of, do 2 computations and I get 2 sub-barcodes? Is there anything known about how they relate? Or, if I compute 1 sub-barcode, assuming the function is 1 Lipschitz, can that tell me something about, a sub-barcode for the function where 5 Lipschitz? Yeah, so I was curious if you have anything to say about this general question.
Right. So there's a trivial n² time algorithm to at least check like whether or not any of your current data like satisfies a Lipschitz bound, right?
Yeah.
You might first do that, right? That's like but the truth is, what you're really saying is like, if I have 2 points, and the function value differs by the distance, right? That's like tight for 1 Lipschitz. And you say, well, okay, then if it's just these only 2 points, right? The max and the min Lipschitz extension agree between these points. It's awesome, right? Except that someone says, actually, the function could be 5 Lipschitz, and then like, who knows what happens in between. In which case, so if you wanted to like put the Lipschitz constant as a parameter in here, it's really straightforward to do. Like I said, you could do it 2 ways, right? One is you just scale the function down, right? So 5 Lipschitz function, you just divide it by 5. Now it's 1 Lipschitz, you win. Okay, but on the other hand, what's going to happen is that'll, of course, decrease all the signal. And so you'll necessarily find less information. And in fact, you will even find, in fact, here's an immediate corollary to some of the theorems here. Let me just, this is brand new results happening right now. So because let's say if there's a 5 Lipschitz extension of F, right, this is going to necessarily be larger than the 1 Lipschitz extension of F, right? So we can apply the same ideas, I guess, and for the min extension as well, right? So right, and so well, actually, let me not even put F in there. Let's forget about F for a second. What happens is this means that if I looked at just immediately, right, I get that the persistence of the computation that I get on the 5 is going to be a sub-barcode for the smaller Lipschitz constant. Right, because it's right, it factors through this.
Cool, thanks.
So actually, you know what that means though? That means that you can also, it also defines a filtration on the barcode if you want, right? So as I increase the Lipschitz constant, right, I get less and less of the bars. Whether that's interesting or useful, I don't know, but that's what you get.
So the bars are shrinking and then some might disappear. Okay.
Yeah.
Cool. Thanks.
Any more questions?
Yeah, can I just ask, just following up on this? So do you have a sense of how easy it would be to compute these F5s here, this filtration of your barcode if you've already done the computation once?
Oh, yeah, good question. Let's see. So it depends on the setting, right? So in in 1D, right, you I don't know. I don't know, it's a good question. I feel like in the example I gave, the construction over using RIPS complexes, you could just store a little bit of extra information about like which was the point that which was the nearest point that determine, like when you're on in the lower envelope of a bunch of cones, you can ask like which cone was I on, and if I scaled all the cones up, I think. Okay, actually, I take it back. I don't know at all. I think it's a good question because you might hope to reuse some of that computation, but I don't know how to do it.
But yeah, it'd be cool to look at this filtration of barcodes. Thanks.
Are there any more questions or comments for Don?
Oh, I have one more question if nobody has more questions.
Please go ahead.
That's okay. So because Don, when you first started talking about this is a posted relation. So I could imagine there is this nice space. Well, okay, one setting is you have Okay, I hope you know where I think I'm going. But if you have, let's say one particular setting is you have a space X, you don't know, but you have some set of points P sample from X.
Yeah.
Now you can take subsample S1, S2, S3 from P, and each one of them is going to give you this sort of barcode, and then there's going to be some sort of sub-barcode relation. And that builds sort of the entire sort of POSIX structure among all the subsamples. That's one potential setting. The other setting is you start with an initial sample S1, and then you add more sample, which is S2, you add more sample, which is S3, which is sort of incremental sample. Again, you have this POSIX, this POSIX structure over your sub-barcode. So the question is that what can you say about this POSIX structure? Would that POSIX structure eventually reflect the property of that underlying space?
Yeah, I think not. And here's an example where it fails totally.
Okay.
It's like, imagine I just have a bunch of features and like one sample samples one of them.
Yeah.
Next sample samples another one.
Yeah.
And they all come out with one bar. Okay. And so if you look at the POSIX on the bars, right, if they're all nested, it's like, oh, well, okay. Have they found just the one bar, or are there many other, is it just one feature, or are there many features?
Right.
So it's hard, like you would need probably some other conditions on the sample, right? Because when you just match them up to say like this is a sub barcode of the other one, remember that it's the usual problem with bars, right? Is that you forgot where they came from.
Yeah, exactly. But let's say I put a little bit more constraint over the underlying space, then there is still the possibility of potentially stitching those sub bars together to say that, you know, exactly the example you said, I have two features, let's say, and I have one sample that recovered one feature and another sample I recovered another feature. Ideally, I would like to do some sort of algebraic operation over those sub barcode so that you know, it's almost like it's a little bit funny, because almost like, you know, globally you have barcode decomposition of the space, but now you are pretty much recovering a subbar of each of those things, and I would like to kind of glue them back together. Is there like a systematic way of doing it in the current vocabulary?
I have no idea. Yeah, I have no idea. I wouldn't rule it out, but I wouldn't know where to make a first step.
Okay. Okay, that was more of a comments, but it almost have a, I guess my comments was more of thinking about if I have a global space, I have bar decomposition, and then your framework is going to say, well, not only I'm going to recover the sub bars of those, but stitching back, I need a little bit more information. But if I have that extra information, I might be able to do the almost like local to global kind of recovery from what you have.
Maybe it's possible. Like I said, I have no idea what the first step. I thought you were going to ask. I got really excited. I really thought because you were asking about the POSIX. I thought you were going to ask about other lattices besides the lattice of Lipschitz functions. So I was going to say, like, if you had another lattice of function, or like a hypothesis space where you can compute maxes and mins, that is meets and joins in the lattice, then like the theory all applies. It just happens to be this is one where we know how to compute it. I think Eris was the question.
Yeah, thank you very much for a great talk. Very interesting stuff. Can you go to your motivation slides again? I just want to have a small comment and question. Yeah, right there. Yeah. So in general, so I'm assuming you have some sample data and you are trying to extend this using the same sample data to find the person's barcode larger than, let's say. Yeah. And at the beginning, I assume that when you do this matching, so I can understand that the birth times in the larger data should be smaller than the birth times of the sample, of course. But the death times of the larger data should be also smaller than the death times of the sample data. This is my first intuition. Okay. So in your setting, this is a comment for the. So when you have your this maximal Lipschitz and minimum Lipschitz extension envelope, you are staying very close to your original set, in a sense. So when I think about the space functions and spaces, I always, so my very geometric intuition says that you can think of this space as a graph space. So take the space and then look at the graph of the function.
Okay.
And then you have an envelope there. But
Exactly.
in general, if you want to approach just the maximal extension of these guys, this matching, instead of using this matching, the sub-barcode is very well working for the envelope guy. So maximal Lipschitz is greater than the maximal Lipschitz is greater than minimal Lipschitz. You are staying close to the original guy. But if you want to extend the whole sample space and your sample space is not very close to, for example, in a very situation, let's say, and then this matching should not work because in general, so geometrically, if your sample space is, let's say, a subspace, a codimension 1 subspace, etc., then the dead times must be greatly smaller than the dead times on the so it should be in the left of the all barcodes. So for the persistence diagram of the extensions, there should be a different approach. But for envelope approach, we think this is very nice. But for the general approach, instead of this, there should be a more general matching should be considered. I mean,
what would be a more general matching? Oh, you mean matchings and not inclusions?
Not inclusions, yeah, because dead times in the larger space should be smaller than that because it should die first in the larger space. If you are just looking at the extension, the whole space. In the envelope space, this is great. This is working very great.
Yeah.
The difference between the maximal extension and minimal extension. But in general, if you don't have a very good approximation of the sample space to the like Gromov-Hausdorff approximation, etc., instead of this, I think one should consider a more general matching here. Dead times should be smaller than in the larger space should be smaller than dead times in this sample space. Geometric intuition. I mean, this is.
Yeah. No, I see what you're saying. I guess, but yeah. So if you just looked at like one extension, like if you just take the max extension, right? Like there's just almost no way you can get arbitrarily bad barcode compared to F, right? Because it's going to have like all kinds of weird stuff. Like you can get like tremendously persistent features that are completely spurious, and it can completely miss features that are actually there. So the individual extensions, it's true, like they're going to be different. It's not just, in fact, it's worse than what you say. It's not just that some of the features will shrink. It's like anything can happen. It's sort of wonderful though that the inclusion of the max into the min cancels all of the noise, like everything that's not there. So it has to, in some sense, it says all that remains is what's legitimately supported by the data.
Can I say one small thing here, Don? Because Barish, I was very confused by this at first too. And I think if you're thinking of just pure Viator-Scripps complexes, I know exactly what you're saying. I feel like Don's maybe in a different setting where Don's most interested in sublevel set persistence. And then these bars in black and red are like what are guaranteed to appear, what's guaranteed from what's known. And so as you sample more in this setting, what you can guarantee to have to appear actually gets larger. So I totally get your intuition, Barish. I just think that Don's setting is actually different. Yeah.
I mean, I see. I'm also talking about sublevel setting, but if you have a feature in the smaller subset, let's say a loop, it can be filled in the larger subset immediately. That's my problem.
Yeah, but Don's setting is what he would draw for the loop is what's guaranteed. And the loop wouldn't be guaranteed because he hasn't sampled in the larger disk, so he can't certify.
Have to get something in the middle.
Yeah.
Or you'd have to have, like, if you have a high values around a circle, you need a low value in the middle to see it.
So Don would remove that circle in his computation of the black bars.
You would just not see it. You wouldn't see
it. Just not be there. Yeah.
Oh, okay. You are just removing that.
You just won't see. Yeah.
Okay. Okay, I see. Yeah. Thank you.
All right, so I'll stop recording right now. But if people want to continue the conversation, that's great. So